Okay, so we're done with chapter 3 now. So we're going to skip ahead to 5. Okay, I think I mentioned the other day that chapter 4 is an introduction to differential equations, which you may take at some point in your math career, but we're not going to do that right here. You can read the discussion in the book if you want to, but we're going to move on to chapter 5, which is our introduction to sequences in series. But before we do that, I think we could use a little bit more practice with the technique of partial fractions that we were using last time. So I picked a few problems for us to look at. So why don't we take a look and see how these work? So first of all, we have the integral of 3x over x squared plus 2x minus 8 dx. All right, so remember, with this method of partial fractions, what we're trying to do is take the denominator and break it down into a couple of component parts. And so we're going to factor x squared plus 2x minus 8. So we're aiming for two values whose product is negative 8. If we can think of these as x plus m and x plus n, whatever we pick for m and n, their product will be the negative 8, and their sum will be the 2, the coefficient of x. There will only be one unique pair of values that will accomplish this goal. So let's think about this. How about x plus 4 times x minus 2? All right, well, here again, here's m, here's n. So let's find out if this is true. If mn equals 4 times negative 2, that is negative 8 as we need. And m plus n is 4 minus 2, which is 2. So we're all set. So that means we can rewrite this as the integral of 3x over x plus 4 and x minus 2. All right, so what do we do now? Well, again, remember, this is partial fractions. So we're going to take this expression and write it in a very interesting way. A over x plus 4 plus b over x minus 2. And of course, our goal is to solve for a and b. Now, of course, we can't directly combine these two expressions because they have a different denominator. So what we need is a common denominator between all three terms. In other words, what's on the left-hand side and what's on the right-hand side. Well, that won't be that difficult. All we have to do is multiply a over x plus 4 times the ratio of x minus 2 over x minus 2. And then for b over x minus 2, we'll multiply it by the ratio of x plus 4 over x plus 4. So the point of this is that all three terms now have the same denominator. Which is x plus 4 times x minus 2. All right, now, because every term here has the same denominator, we can simplify this by simply setting the numerators equal to each other. In other words, the numerator of the left-hand side equals the numerator of the right-hand side. And you can prove this just by multiplying both sides by x plus 4 times x minus 2. All right, now we're going to drop these parentheses, ax minus 2a plus bx plus 4b. So our goal is to gather up all the like terms All right, and then we'll set them equal to the left-hand side of the equation. So in other words, on the left-hand side, we have 3x. Think of it as 3x plus 0. And this tells me that 3 equals a plus b. Okay. And 0 equals minus 2a plus 4b. Okay. So in other words, what we're doing is setting to each other the coefficients. Okay. So our job now is to figure out some clever method to figure out both a and b. So on this, let's say we come over here and add 2a to both sides. That implies that a equals 2b. And once we know that, we can plug that in over here. 3 equals 2b plus b. 3 equals 3b. Yes, so therefore b equals 1. That's right. So what that means then is that we solve for a and b. Oh, you know what I just realized? We still have to do a. Sorry, a equals 2b. Means that a equals 2. All right, now we're good. We need a constant for both of them. So now you can go back to original expression. Sometimes it works, sometimes it doesn't. Okay, so a is 2. Well, actually, this is not what I wanted. Hold on. Sorry, I copied the wrong thing. This is what I was after. So keeping in mind that a is 2 and b is 1. So this implies, after all of this, that the very original equation that we had is the same thing as okay, in other words, they are the same thing. Algebraically, they equal each other. So what we've done is we've taken a complicated integral and reduced it to the sum of two relatively straightforward integrals. Each of which can be solved directly with u substitution. All right, so here let's let u be x plus 4 so that du is simply dx. And over here, u would be x minus 2, and du would again be dx. So you've got 2 du over u plus du over u. And so you end up here with 2 log absolute value of u plus log absolute value of u. If you notice, we don't add the constant until the very end when we actually need it. Okay, in other words, all of these could theoretically have constants next to them, but we can save this to the end because all the constants will be consolidated anyway. And so finally, after all that, we have 2 log absolute value of x plus 4 plus 2 log x absolute x minus 2 plus the constant. And I think I mentioned the other day, if you're not sure, you can feel free to double check. If you differentiate this with respect to x, it'll bring you back to this expression on top. So that's a classic partial fractions problem. Okay. Some of them are messier than others, but that is how the process basically works. So let's try this one. So x squared minus 4 can be factored into x plus 2, x minus 2. Whenever you see a difference of two squares like that, you're going to end up with two factors that are x plus and minus the same term. So we can write this as this. All right, now what do we do? Same thing as the last problem. Okay, this one is very similar. We have so we need a common denominator for both sides of the equation. We'll multiply this term by x minus 4 over x minus 4. And here I'll have x plus 2 over x plus 2. All right, so since now all the terms have the same common denominator, we can just write this again in terms of the numerators. And we're going to gather together like terms. All right, so that means now, of course, you notice the coefficient here is just 1. 1 equals the a plus b. Because you can think of this x by itself as simply 1x plus 0. That implies also that 0 equals the constants minus 4a plus 2b. 4a equals 2b. A equals 1/2 b. And since that's the case, 1 equals 1/2 b plus b. 1 equals 3/2 b. That means that 2/3 is b, and that means that a is 1/2 of that. One-third. All right. Okay. I'm just going to double check. Yeah, that's it. Okay. So now, again, based on this expression, oh, I forgot to make the substitution. A is 1/3 and B is 2/3. Okay, so you can see both of these could clearly be done with U substitution. So we're done. Okay, good. All right, what else do we have here? Let's try this. Okay, so this one can be rewritten as 2 minus x. Okay, so now we use our favorite technique. Um, all right, so now we need a common denominator. And of course, now that they have the same denominator, we can just set the numerators equal to each other. Okay, so we have two terms on the left. So negative x equals, this means that -1 equals a plus b, because those are the coefficients on the left. The coefficient of x is -1, on the right it's a plus b. And this also tells us that 2 equals a. So therefore, that indicates that -3 is b. All right, so all right, so the integral that we need can be rewritten as all right. So again, this is straightforward U substitution, except that no, it's just normal U substitution. Here you would have U is x, du is dx. Here you'd have U is x plus 1, du is dx. Very good. All right. Let's see. Probably one or two more just to see what happens. Here is one. Oh my God. So this one involves trigonometry. That's always a lot of fun. Well, maybe not. All right, let's try this one. So we have the integral of sine x over cosine squared x minus, sorry, plus cosine x minus 6. Now, let's see if we can use u substitution. Let's try this. Before we do anything else, before we even try partial fractions, let's see if we can simplify this a little. Ooh, see now the problem with this is that this definition of du requires cosine x dx, and we don't have that. So let's not try this one. Let's try u equals cosine x, and du would therefore be minus sine x dx. Okay, we don't have that either, but we're only missing the negative. Okay, so in other words, if we rewrite this, let's move the dx up here. We're in good shape now. All right. Now, I think you can see what's going to happen if we rewrite this. All of a sudden, now, even though we've switched the variable from x to a, we can now apply partial fractions. Very clever of us. Okay. In other words, what we're able to do is take a very messy expression and turn it into something that where we can apply partial fractions. So what we're going to do is this. And then we'll proceed along our normal lines. Actually, I'll tell you what, just to make it less, let me do this, just to make sure it's clear what we're doing. Yeah, I'm going to rewrite this slightly just to make sure that we don't make any mistakes. Because this is what I want to compare to a over one factor plus b over the other factor. So let's, I mean, I could have saved the negative for last, but I think it'll be easier this way. Okay. So we need a common denominator, as always. Now we set the numerators equal to each other. Gather up the like terms. Okay, so in other words, we don't have any u's on the left-hand side. So that means that 0 equals a plus b. The constant that we have is -1. So let's do this. Subtract b from both sides. So -1/4 is b, which implies that a must be +1/4. All right, so the original expression in terms of u's, so we ended up with a over u plus 3, 1/4 over u plus 3. And then b is -1/4. That's divided by u minus 2. All right, so this is what we're after. No, it's not. Now, even though the variables are u's, we can still use u substitution. This one becomes 1/4 log u plus 3 minus 1/4 log u minus 2. And now, if you recall, u, we chose cosine x. Okay. It's a bit of a mess, but there it is. So this one is extra complicated because it involved, both u substitution and partial fractions. All right. So now we're ready to dive into something completely new. Chapter 5, that is. And just save this. And let's take a look. Now, what is going on in chapter 5? Now, this is a very interesting topic because it technically this is where we kind of overlap between calculus and what could be called either discrete or finite math. The concepts in here can be used for a lot of different applications. And so it's very different than what we've done up to this point. We'll start with the sequences and then we'll work our way up to the series. Along the way, we'll also see some very interesting theorems that help us understand how limits behave. So the logic behind understanding sequences and series is that they can often let us reduce the complexity of a problem that we're working on and derive results that otherwise would be extremely difficult. All right, so first things first, the sequence is a very simple concept. You can think of it as an ordered list of terms. Each one of these is a term. We're using A with a subscript to represent the terms. The subscript lets us keep track of their order, because here the order is very important. Now, before I go any further, I just want to remind you that somewhere along the way in your travels, you were almost certainly introduced to a very special type of sequence, and that was the Fibonacci sequence. And so it goes like this. So the whole point of this is that there's a pattern here. This could be thought of as A1, A2, A3, et cetera, et cetera. Specifically, what's happening here is that after the first two terms, each term is the sum of the previous two terms. Each term is the sum of the previous two terms. Those two is the sum of 1 and 1, 3 is the sum of 1 and 2, 5 is the sum of 2 and 3, et cetera, et cetera. So when it has a pattern like this, where each term is a function of one or more previous terms, this is referred to as a recursive relation, which we'll discuss more in a few minutes. And now, as it turns out, there's a formula that I won't show you here, but that you could actually use to calculate any term in the sequence. It's a very messy formula, but it does exist. So in other words, you could have a formula that says term X has the following value. So it can be written as a recursive function or as directly as an explicit formula. But the idea here is that it's a sequence because we have a string of numbers in a particular order with a specific pattern. So the ones we'll be looking at are not typically quite as complicated as that. Now, what we're going to be able to do here too is the notation, rather than writing this every time, this is the more formal way of writing this. We have AN, A is term N, the index is N, it ranges from 1 to infinity. Okay, so in other words, this is just another way of saying everything from 1 to infinity. Okay, so by the way, even though this thing superficially looks like a set, the difference between a set even if it's an infinite set, and the sequence, they may superficially look the same. Is that with the set, the order in which these terms appear is not relevant. It doesn't make any difference to the set. The set's value doesn't depend on the order in which we list the items in it. Whereas with the sequence, it makes all the difference in the world. In other words, the sequence itself is a pattern of some kind. It forms some kind of a pattern that we can observe, and often we can turn that into some kind of a formula so that we can figure out what each term would have to be without having to write them all out. Now, many times the sequence runs from 1 to infinity. It doesn't have to, though, but you might recall the definition of the so-called natural numbers. Sometimes these are called the counting numbers for obvious reasons. And it's an infinite set. And basically, it's all the positive integers. So if your sequence is indexed 1, 2, 3, et cetera, then we can make the case that the domain of the sequence is the natural numbers. Okay, now what if it doesn't start at one? Well, there are other sets that we can map this to. Just as a quick example, you might recall also that we have the whole numbers. Which is basically just the natural numbers plus the zero. And you do sometimes see sequences that begin with zero. For some applications, this makes more sense than starting with one. Okay, so in other words, there's nothing to stop the indexes from starting at zero. And in fact, you might even run into cases where they're negative. But usually it's just 1 to infinity, 0 to infinity, something like that. Now, if we have a pattern, if we can find a pattern with our sequence, what we can do is actually just write it out as a formula. Like, look at this one. This is clearly 2 to the first, 2 to the second. Oops. So why not write it like that? Why not take advantage of that? If the indexes are 1 to infinity, well, you've got a very nice formula here, 2 to the nth power. That's it, because all of those terms are 2 to the power of n. And so that means all of this writing can be replaced with this expression. Sometimes the formula can be very, very messy, though. But it's nice to know that you can do this. Now, if the terms are related to each other somehow, we may be able to express them in that way by creating what's called a recurrence relation. And so here, we notice that every term is double the one before it. So instead of writing this as a formula, we can write this. So for any term from 2 up to infinity, each term is simply double the previous term. So if you notice, here's n minus 1. So this is the previous term. So for 2, 4, 6, 8, what did I do? 2, 4, 8, 16, 32. This is A1, A2, A3, A4, A5. That means that, for example, A3 is 2 times A2. Okay, so in other words, 8 is simply 2 times 4. A5 would be 2 times A4. So we can call it a recurrence, or sometimes you hear it called a recursive relationship. It means the same thing. In other words, the terms are a specific function of the previous terms. Now, the Fibonacci sequence is actually the sum of the previous 2 terms. So if you want to go back and revisit that, what you could do is just say, well, listen, after specifying that A1 and A2 are both 1, then you would say that AN is simply AN minus 1 plus AN minus 2. And then you would write here something like N is at least 3. And that's how you would know. Starting from term 3, it's just the sum of the previous 2 terms, where we define the first 2 terms to be 1s. By the way, there's many others that you probably never heard of that, these show up in math all the time, but this one happens to be one of the more popular ones. It turned out that this there's a very famous number called the golden ratio, which basically can be derived from the ratio of consecutive Fibonacci terms. And it appeared in a very famous novel called the Da Vinci Code, as it was a very important part of that novel. So if you've heard of the Da Vinci Code, this Fibonacci sequence proves to be extremely important in the plot. But I don't want to spoil it for you. You can go look into that yourself. By the way, Fibonacci was a contemporary of Leonardo da Vinci. They may not necessarily have met each other, but they certainly were aware of each other's work. So, Fibonacci was a very famous mathematician in his day. And at one point, Da Vinci had another friend who's a mathematician, and Da Vinci actually illustrated his book for him. Okay, he's like, fine, you want to write a book about math? I'll draw whatever you need. But anyway, so as we've already seen, the sequence can start at 0. All right, now we're going to classify sequences as geometric and arithmetic. Now, obviously, not all sequences are either geometric or arithmetic, but many of them are. And these are among the most important ones that we'll see in applied fields. So we want to know what they are and what their properties are. So we have arithmetic and geometric sequences. And so they're very straightforward concepts. An arithmetic sequence is one in which the differences between the consecutive terms are constant. Let's look at a few quick examples. In the first case, we started with the 1, and then every term after that has 1 added to it. If you want to think about it in terms of a recurrence relationship, each term is the previous term plus d in an arithmetic sequence. And in this case, that difference is 1. So you could define this by saying a1 equals 1. And then from n is greater than or equal to 2, an equals an minus 1 plus 1. That's how you define it as a recurrence relationship. We start with a 1, and from 2 on, each term is 1 greater than the previous one. And in this case, we have 3. If you notice, the term, it doesn't have to start at 1. It can start anywhere. And not only that, look at this last one. The difference is actually negative. The terms do not have to go up. They could go down. So, really anything goes with sequences. All right, now here's another one. Now you can see here that the first term is 3, and the common difference is 4. Okay, now, by the way, if we know these two terms, we don't need any other information. As long as we have this, we're all set. That's all we need to uniquely identify all the terms in the sequence, because the mere fact that we're being given a difference proves that this is an arithmetic sequence. All we need to know then is what is the difference and what is the first term. So formally, you can write this in a looks very formal. A1 is 3. Each term is equal to the previous term plus 4 because d equals 4, starting with term 2. All right. So we can write it like this. Again, any term past term 2, here's term 1. Any term past that is equal to n minus 1 times d. Okay, so let's say for that last case, 3, 7, 11 If I wanted to know, let's say term 4, it would be A1 plus 4 minus 1 times D, which is 3 plus 4 minus 1 times the common difference of 4. And it is indeed 15. Yes, this is the fourth term. And this is true for any arithmetic sequence, at least that start at 1. Okay, that's understood. I mean, if it starts at 0, then you have to change it. But for any arithmetic sequence, where the index starts at 1. All right. Now, we can also define a very convenient formula. Now, this is really going to save us some time to add up the first n terms in an arithmetic sequence. So that Sn means the sum of the first n terms. Now, this is going to be very helpful, as you can probably imagine. In order to do this, we need the first term and then the last term, because here we're only looking at a finite number of terms, n. And then we need to know the number of terms, and then divide that by 2. So let's say that our sequence is 1, 3, 5, 7, 9, 11. So A is 1, A1 is 1. The common difference is 2. What if they want to know first 5 terms? Okay, so let's get this formula back. Oh, one more thing we'll need. If we're looking for the first 5 terms, we need A5, which you can see here is 9. So A1 is 1, A5 is 9. $25. Now, you can manually check this. And you'll see they do add up to 25. Well, and the beauty of this formula, it works no matter how many of their terms there are. You could, for example, let's say you're interested in adding up for this sequence. Ooh, the first 100. So A1 is 1. Now, clearly, because the common difference is just 1, A100 is also 100. $50. So you can see it saved us an enormous amount of time. And it works. All right, anyway, so here's another one. So for this arithmetic sequence, A1 is 8. The common difference is 2. What's the sum of the first 6 terms? So that means we need A6, which you can see here is 18. I forgot to write down. N is 6 because we're looking for the sixth term. The sum of the first 6 terms. And that adds up to 78. And of course, you can test this by manually adding them up, and you'll see that that is correct. All right. So then I just mentioned that the second type of sequence that we run into often is the geometric sequence. So I think man, we had so much fun today. The time really went fast. I think we'll stop right here, and then when we pick it up again, we'll go through geometric sequences. So see you all next time.